So, welcome back and let us get started with the CTL model checking algorithms for checking nested properties. So far what we had seen was that how we can check properties which have a single E and any of the temporal properties like X, G or F. Now let us start by looking at this kind of a property, that we have the property EF, P and EG not Q. Okay, so this EG is nested within this EF. Now for CTL it is very simple. What we do is we start with the innermost properties, find out the state sets satisfying those properties and then use those state sets in computing the set of states satisfying the outer property. Right. So it is not like that we start from the initial state and try to do this. We basically start from the set of states which satisfies the innermost property and then work backwards to find out all states satisfying the given property. So for this what we are going to do is we will first say that okay, we need to do EF of this thing, okay, and then again decompose this further by saying that we need to find the set of states satisfying P and we need to find the set of states satisfying EG not Q, and then to solve this we need to find out the set of states satisfying not Q. So now having done this decomposition, we will start from this one. We will find the set of states satisfying not Q, then find the set of states satisfying EG not Q, find the set of states satisfying P, then find the set of states satisfying P and EG not Q, and then find the set of states satisfying this property. Okay, that is the way in which we do it. So this is standard dynamic program. Right. We start from the smallest components, solve those components and build them up to find out the solutions to the main property. So that is what we do. So let us look at an example here. So in this state machine, the yellow colored states are ones which satisfy P, the blue colored states are ones which satisfy Q, and the red ones are ones which satisfies not P and not Q. Okay, and the property is this one, that EF, P and EG not Q. So we will start with the set of states satisfying Q and then find out the set of states satisfying EG not Q. So this is the set of states. Which are the set of states which satisfy not Q? The red ones and the yellow ones. Okay, so the red ones and the yellow ones. So this is the set of states satisfying not Q, right? And now we want to find out EG not Q. This is the set of states satisfying EG not Q. Now if we go back one step, see, for EG not Q, it is not just sufficient to have not Q here. It has to be in a cycle where we have not Q, right. So out of these states, which ones are in a cycle? So it is these ones which are in a cycle. This one is not in a cycle containing not Q, okay, because it has to go to these blue states, right. So this is the set of states. Also this one is not in a loop containing only not Q states. So this is the set of states that we will arrive at by computing EG not Q. Now next thing is we have to take the intersection of this with the P states, because we need P and EG not Q, right. So which ones will be left? So only the yellow ones out of this region. So this one, this and this. Okay. this is P and EG not Q states. Now we need all states from which these states can be reached, because we want EF of this, right. So these states obviously will be there. In addition, this one will come in because we can reach this, this will come in because of this transition. Any of the other ones? I do not think so, right. There. This is the set of states satisfying EF, P and EG not Q, right. Complexity. The complexity of CTL model checking is linear in the size of the model and also linear in the size of the CTL formula, right. Why do we say it is linear in the size of the CTL formula? Because we do this decomposition, and for each sub formula we have to do one of those fixed point computations, right. For example, for this property we had to do one fixed point computation for this, right, and one fixed point computation for this one, right. So the number of fixed point computations is linear in the size of the state space, okay. And what is the complexity of each of those fixed point computations? It is linear in the size of the state machine, because what we are doing is essentially doing a DFS, right. DFS, BFS or whatever, we are traversing the state space only once for each of them. So if M is the size of the model, F is the size of the formula, then the complexity of this is, compare this with LTL. For LTL, this is not F but 2 to the power F, because there the complexity was exponential in the, for LTL model checking algorithms, exponential in the length of the formula. But still, in all of these problems we know that this is the main issue, right. It is because of this size that we run into capacity problems. Fairness. Fairness is defined as follows. Fairness F is a set of states S1, S2 through Sn, and a fair path of a model is a path which visits the states in F infinitely often. A CTL formula F is true under the fairness constraint if F is true only in the fair paths of the model. Okay, if we only consider the fair paths of the model and F is true in that restriction of the model, then we say the CTL property is true under the fairness constraint F. Okay. Now look at this thing. If you look at AFG1, along all paths in future G1 must hold. If you look at this particular, this is a starting state, right. Does this hold? No, because it can always continue, there is a path in which it can always go on in this, right. Now in that case this is not going to hold, right. Now remember that this is computation tree logic. What is that computation tree? If you start from this state and enumerate all the paths as a tree, then that is a computation tree. So in that tree there is one branch which goes along in this forever. It is an infinite tree, right. So, therefore, we must now let us see what happens if we produce the fairness constraint which says R1 is asserted infinitely often. Now, when we say that R1 is asserted infinitely often, then we see in this R1 is asserted, okay, in this R1 is asserted infinitely often, but if you land up in this state, then R1 is not asserted infinitely often, right. So, under the fairness assumption that R1 is asserted infinitely often, this becomes the restricted structure, only the dashed edges, right. Now, if you look at this restricted structures, then AFG1 is true under this, okay. Now, in terms of fairness, when you say R1 is asserted infinitely often, it means states satisfying R1 must be visited infinitely often. So, here states satisfying R1 are which ones? This is the states S0 and S2. So, the fairness F is S0 S2. Under the fairness S0 S2, this property AFG1 holds on this restricted Kripke structure. Is that clear? Right. Now, why do we want to have fairness in CTL model checking? Because we want to express things like that there are certain assumptions about the environment behavior, and we want to check the property under those environment behaviors. So, that the fact that R1 is asserted infinitely often is one of those behaviors. So, the formal semantics of fairness is like this, that a fair Kripke structure is a 6 tuple where we have these in addition to the usual stuff, we have this F, okay, and this F is a subset of the set of states, okay. It is a set of fairness constraints. Let pi be a path in M, and let INF pi, as we described previously, be the set of states in S, set of states that are visited infinitely often, okay. Now, we say that pi is fair if and only for every element P belonging to F, INF pi intersection P is not equal to empty. Now, see that this is one fairness constraint is a set of states. See, if you go back here, what was this fairness constraint, that R1 is asserted infinitely often? This fairness constraint is this one state set S0 S2, right. So, if you have k different fairness constraints, you will have k such state sets, okay. That is why this is a subset of 2 to the power s, which means that it is a subset of the power set of S. So, this is a collection of state sets. Each state set corresponds to a fairness constraint, and a path is fair if all the fairness constraints are satisfied, right. So, that is what is meant here, that for every element P belonging to F, what is P? P is a set of states. For every fairness constraint in F, which is represented by a set of states, the intersection is non-empty, which means that at least one state from that fairness set should be visited infinitely often, right. Now, what the CTL model checker does therefore is that it has these fairness constraints, and you have those algorithms for finding out the set of states satisfying different properties, right. It imposes the fairness constraints and then checks those properties on the fair Kripke structure. Now, let us go back to LTL model checking. What were we doing in LTL model checking? We were taking the property, constructing a automaton out of it, taking the product of that automaton with the implementation, right, and we have a set of accepting states which must be visited infinitely often, right. Now this becomes very similar at the end, last part becomes very similar to CTL model checking with fairness, right. What will be the fairness constant? Your set of accepting states, the set of Bookie accepting states will become your fairness constant. And what property are you going to look for? What property are we going to look for? You want to look for whether there is any infinite path which in the fair Kripke structure, right. So let me note it down. For LTL model checking, what we did was we took the machine M, we created the automaton for B not phi, we take their product, okay. For this product, then we want to search for that given where F is the set of accepting states, we want to see that find a path which visits some state of F right. So what do we do? Let us suppose that this product state machine is R. So what we do is we CTL we will use a CTL model checker, okay. So the fairness constraint will be this set F, okay. So R is the Kripke structure, F is the fairness constant, it is going to find out the fair Kripke structure. What we want is whether there is any path in that, whether there is any infinite path in the fair Kripke structure. If there is any infinite path in the fair Kripke structure, then that is a path which goes through states in F infinitely often, right. So what do you look for? You just look for the property whether EG true. What is EG true? It just looks for any path in the Kripke structure, right. You don't, it does not have to satisfy anything, just true, right, unconstrained. It just looks for an unconstrained path in the infinite path in the EG, because it has to be an infinite path, right. So you have to have some cycle in it. Is this making sense? Are you getting what I am saying? We want to transform the LTL model checking into the CTL model checking problem. What we have done is we have created the Bookie automaton of the negation of that property, taken its intersection with the implementation M, and constructed another automaton R. This automaton R will be the Kripke structure for the CTL model checker. Okay. But every path in this Kripke structure is not an accepting run of this automaton. It is only those runs which go through states in F infinitely often. So, we take this F and pass it on as the fairness constraint to the CTL model checker and say that, look, this is my Kripke structure R, this is my fairness constraint F, and I want to solve the property EG true. In other words, please find a path in the Kripke structure. EG true is any path in the Kripke structure which exists in the fair Kripke structure. So, in the Kripke structure under the fairness constraint F, because if there is such a path, then that is a path which is an accepting path here, right. So, that is how you have a core CTL model checker and you can actually transform this LTL model checking problem to a CTL model checker, right. All right. Now, there are various approaches that people have taken towards this, the LTL and CTL model checking. The main intention of all this is to reduce the computational overhead, right. Now, we know that CTL model checking is linear in the size of the machine and the size of the property. LTL model checking is p-space complete, right, but it is, we have algorithms which are exponential in the size of the property, but linear in the size of the state machine. Now, the whole issue there is that how do we manage the state machine. So, broadly there are a set of different approaches which people have taken. Okay. First one is that we could use BDTs to represent the state transition relation, and then we use this pre-image computation and fixed point computation to find out the set of states satisfying different properties. And we now know that how to transform the LTL model checking problem into CTL model checking problem and solve it using the CTL model checker. Besides BDTs, so BDT based model checking, which is now this is sometimes colloquially referred to as symbolic model checking, but symbolic model checking is actually means that we have a symbolic method for doing the model checking, right. So, it has, strictly speaking, that symbolic model checking is not something which is related to BDTs, it is actually larger than BDTs. So, BDT based model checking is one of the symbolic model checking approaches, but in the original the papers in which the BDT based model checking algorithms were presented for this first time, they referred to the technique as symbolic model checking, and that is why people colloquially started referring to BDT based model checking as symbolic model checking, right. But thereafter we will go through this in a little bit of details. There was the notion of SAT based model checking, okay, where instead of using BDTs we will reduce the model checking problem to Boolean satisfiability, okay. So, that approach, so under this there is the bounded model checking approach, which, or BMC. Again you see, bounded model checking basically means that we want to check the truth of the property up to certain temporal bound. So, I am going to look ahead for up to maybe k cycles and see whether I can get a proof or a refutation of the property within those k cycles, right. So, that is what is meant by bounded model checking. Again, it does not have any direct relationship with SAT, but SAT based model checking algorithms, they work with these bounds, and you can use BMC with SAT. So, that is why, you know, again colloquially people try to relate these two, but philosophically bounded model checking is only working the model checking algorithm with certain bounds. So, there is no reason why that should be anything to do with SAT, but SAT based model checking algorithms typically work with these bounds. So, they are BMC approaches. We are going to look at these two in some details. The another way of doing it is what is called the automata theoretic what you do here is, again you see this is also the methodology that I am going to talk about here again is colloquially related to automata theoretic approach, but again philosophically it does not have to be that way. For example, what people do here is that you take the property, you take the Kripke structure, and then instead of computing the product, you compute the product on the fly. So, what you do is that you do a depth first computation of the product, right. Are you getting what I am saying? You do not explicitly create the two state machines and take their product. You have both state machines in an implicit form. We do not create the expanded graph of the state machine. Rather, we have this state transition relation corresponding to the implementation, we have the state transition relation corresponding to the checker automaton, and then we systematically do a depth first traversal of the implementation and check the property on each of those traces, right. Now, note one thing is that when you are looking for GP, a property like GP, if you are going depth first, so you get P, you get P, you get P, and then suddenly you find a loop, right. When you find a loop, then you know that GP is true in this path, right. So, in your depth first traversal, you keep on seeing whether you have already reached a visited vertex or a loop, you have looped back to a vertex, and then you can take a decision about the truth of that property at that point of time. Okay. So, this is the way in which this on the fly model checking approach works. Okay. So, these are broadly the three core approaches that are followed for model checking. In addition to this, there is a whole lot of techniques that have come up to reduce the size of the state space, and we can reduce the size of the state space in a variety of ways. Okay. One of them is that we only try to prune out all those parts of the state space which is not necessary for proving a particular property, right. We use assumptions about the environment to prune out the state space, and there is also a technique called counter example guided abstraction refinement, in which I will talk about in a little bit, because that has become a very core part of model checking today, in which you start with a very abstract version of the state machine, prove the property in that. Okay. If you are able to prove the property, then the abstraction is constructed in such a way that it guarantees that the property also holds in the actual state space. On the other hand, if you get a counter example, then there is another technique by which you check whether the counter example is real. In the sense, is it the case that the counter example is only there in the abstraction but not there in the actual state space? If so, then we have to go back to the abstraction and refine the abstraction so that this spurious counter example does not come again, right, and then again run the checker. The advantage of this is that you are always trying to prove the property on an abstract state machine. So, the chances are that if it holds, then in many cases you will be able to prove the property with an abstraction which is much smaller than the actual state space, right. And this in practice works pretty well because properties typically do not need the entire behavior of the entire design. It requires only some part of the behavior of the whole design. So, if the abstraction can capture only that part, then you can nicely prove the property on that part. Okay. So, we are going to look into that a little bit in as philosophical way as possible. So, the first thing that we will look at is the cone of influence reduction. Okay. This is a very the first cut thing that people do in model checking tools. So, this is the original circuit, okay, and let us say that we want to prove the property that always R1 implies next G1, okay, R1 implies next G1. Now what we do is that we take each of these signals and we try to see whether they are in the cone of influence of these signals. So, does R1 affect this property? Yes. So, R1 stays. Does G1 affect this property? Yes. So, G1 stays. Can R2 affect this property? No, because R2 in no way can influence the value of G1. Okay. R2 cannot influence the value of G1, R2 cannot influence the value of R1. So, R2 is not in the cone of influence of this property. Is G2 in the cone of influence of this property? No, because G2 can in no way influence R1 or G1. Okay. So, these two drop out. Okay. Now, we reduce the state machine by dropping R2 and G2. Now, think of the state machine. How many states did it originally have? 16 states. Why? Because 2 state bits and 2 input bits. So, in the non-deterministic state machine, we would have 16 states, right. Okay. Now, those 16 states have what? R1, R2, G1, G2, right. Now, in that state machine, we are dropping the R2 and G2 variables, right, and creating an abstract state machine. All right, that is the cone of influence reduced state machine. So, that state machine will have only this. This part of the circuit will be eliminated, and it is only this one that will remain. And this state machine has only 4 states. Why? R1 and G1. These are the 2 state bits. So, we have 4 states. Is that clear? Now, every time we will not be so lucky. For example, if we had a property which involved R2 and G2, then let us see, then R2 will stay, G2 will stay, R1 will also stay because R1 can affect G2. Not only that, G1 will also stay because G1 also can affect, right. So, if there is a property over R2 and G2, then we will have to keep all 4 of them, right. So, we will not get any cone of influence reduction. Now, in a large circuit, when you are looking at a property which has a small cone of influence, this is a very useful reduction, because it throws away a lot of the circuit and only preserves your cone of interest, right. How do you compute the cone of influence? For a variable, you start with that variable, work backwards across the flops, right, until you have found out every variable in the cone. So, for example, to find the cone of G1, we have R1 in the cone of G1, then we do not have anything else in the cone of G1. If you look at the cone of G2, then G1 is in the, we work backwards. So, if we work backwards along this, then we find G1 is in its cone. Then when we work backwards along this, we find R1 is in its cone. We find like this, that R2 also is in its cone, right. So, that is how you do cone of influence reduction, just by traversing the circuit and determining this. No state space traversal is done here, only traverse the circuit and find out what is the cone of influence. Right. I think okay, before we go into bounded model checking, let me just, I will talk of this in the next class. Okay. So, in addition to the BDD and SAT based tools, we have on the fly FPV tools, which I just now mentioned. These are called automated theoretic on the fly FPV tools. It creates the checker automaton, and the emptiness search is done depth first, thereby saving space. And it treats model checking time for space efficiency, right, because you do not create the product explicitly, rather you do a depth first traversal. There is one thing which I missed out, is that there are some ATPG based FPV tools. Now, from your testing course you know what ATPG is. So, the idea is pretty simple. We take the checker automaton, okay, we take the RTL, and then what we do is we synthesize the checker automaton as a non-deterministic FSM, a behavioral state machine, okay, and then we want to find out whether the checker automaton output and the RTL output will differ at some point of time, right. So, what we are effectively doing is we are embedding the checker inside the design, and then we are doing an ATPG to see if there is a difference in the output, right. In other words, you might also think of it like this, that you take the negation of the property, create an automaton for that, make it part of the design, and then check whether its output can ever be 1, because if its output can ever be 1, then the negation of the property is satisfied, right. So, basically in that part of the circuit which represents the output of the checker, you look for a stuck at 0 fault, right. So, if you are able to find out any test pattern by which that becomes 1, then for that inputs the circuit actually refutes the property. Is that clear, Anvesh? So, now this is not going to be a complete proof procedure unless we have 100% test coverage. Now, it may so happen that there is a test pattern which can cover that fault, but you are unable to determine it, right. So, then you do not know the answer to the property checker, whether it is true or not. So, what we will do is we will stop here today, and then in the next class we will look at bounded model checking, okay, and we will look at how people manage to add different types of constraints in different ways to keep the state space contained. Having done that, the only other part that will remain in the formal property checking is the counter example guided abstraction refinement approach. Okay. After that, we will go into different things. Okay. Thank you.